before I move on, I want you guys to, if you have your book here, fine. If not, take a look at it at home. I want you to look at page 558 and look at figure 36.7. It's important that you understand that figure.
Page 558.
Yes, because it explains very nicely what is going on with gas field detection. What you have is more steep.
Page 558.
All right, and what that graph is showing you, something like this. All right, and this is called the R section. This is the ion chamber proportional counter. This is the Geiger Muller area. All right, and the first, I don't know if you go back and look at your notes, but the first, I don't know if it was exactly the first, but it was one of the first things that I had mentioned to you last time is when you're looking at gas field detectors, the engineering, the physics behind it is the same. What I said is that what changes is the voltage that is run through it. Remember that? That's what makes it different. All right, and that's what this graph is going to explain to you. As the voltage increases on the chamber in their they call it relative output signal. Or the sensitivity in which the detector can detect radiation goes up as well. Okay, and so you increase the voltage, and then they become more sensitive to radiation. Being more sensitive, it doesn't mean that it's accurate. Not the same thing. Okay, what it's saying is that yeah, you can pick up radiation, but maybe what you're telling us, what you were seeing is not very accurate. Make sense? All right. And so in this area here, this is called the recombination area. That's why it's called R. All right. And what happens in this area is that if the ion chamber is exposed to radiation, what you have is the molecules and the ions. You break the molecule, the ions go separate ways, and then boom, they recombine. That's why it's called the recombination area. So you don't get any reading. Okay? You increase the voltage a little bit, and then you get into the area of the ion chambers, the ionization chamber. And you know you have some sensitivity, very accurate though, somewhat accurate. Okay? So you can tell. You know, you can measure, you can go down to one millirad. You know, that's how sensitive they are. And the exposure times they can be very short. This is the type of device that is used to calibrate X-ray equipment. And so it has to be calibrated not only geared towards the energy of the X-ray equipment, but it's also to the timing. I mean, remember, some of the exposures we do are 1 millisecond. So very short exposures, and so they are very sensitive to that. Okay. And like I said before, there are many designs, there are many different shapes that you can have, how all these devices are built. If, for example, go online today after class, just, it'll help you. And find, and just type, Google it and type ion chambers and proportional counters and Geiger Muller. you're gonna see there is a whole variety. I mean, do it individually. You will see there is a whole variety of shapes, forms, uses, okay, sizes. So it's not one shape, one type. Depending the use that you're doing, depending what the work that you're doing, that's how the shape is. But the principle is the same. Okay? And so what is important to remember is that as the voltage increases, then they become more sensitive. They can catch radiation very quickly. And why is that? Because say you have one X-ray photon coming in, breaks a molecule, okay? Molecule is broken apart, then you get ions out of it, right? Okay, and so, and there is an attractive force from the wall and from the central electrode to attract those ions. Okay, and so very quickly the ions are attracted. There is no recombination, or if there is recombination, it's minimal. Also, as the voltage begins to go up, especially when you're getting into the high end of the proportional counters, and Geiger Mullers too, what you have is that when you have an ion flying to the central electrode, it can also break down other molecules. Make sense? So you don't have, and that's why they are not so accurate, because you don't have one photon creating the ionization event, but you have one photon creating one ionization event, and from that ionization event you can have a chain reaction of other ionization events. So that's why not very accurate, but sensitive. Like, see the difference? Everybody? Good, I'm glad you get it. And so, as you increase the voltage, that's what happens. And by the time you get to the Geiger Muller area, you create lots of ionization events. So, you have, say, one photon, you break a molecule, you get ions out of it. And then you have those ions that are created here, they hit other molecules, and they break other molecules. These molecules break other molecules and other molecules, and so on and so forth. Make sense? Dennis?
I'm sorry, can you please repeat why it's not as accurate? I got a little lost.
Because in the case, let's go back to ion chambers. You have one photon hitting a molecule, okay? Breaking the molecule apart. And then the ions, one will go, the positive ion will go to the wall, the negative ion will go to the central electrode.
Okay.
One to one, let's say.
Okay.
Okay, it can be different, but let's imagine, this is easier to think about, is a one-to-one type of reaction. What do I mean by one-to-one? One photon, one molecule, two ions.
Got it.
Okay. If you increase the voltage, what happens is, when the ions break, remember, ions, what are ions, guys? Charged particles. Okay, charged particles. And so they have a charge. They have either a negative or a positive charge. And when they are moving towards, say, the central electrode, they can break, because of their charge, they can break other molecules. And these other molecules break into ions. And these ions hit other molecules and they break into ions. So you create a chain reaction.
Got it. Okay.
Okay? Anybody else?
Yeah, can you explain for me why is it more sensitive and less accurate? Less accurate because very messy in the.
Exactly, and that's why it's less accurate. What does accuracy mean?
It means precise.
And what is the meaning of precise?
This is the focus.
You need to use other terms. Don't use synonyms. Use other terms. Explain it to me. And that's for everybody. Anybody. What is accurate?
Accurate.
Okay.
Representative?
Huh?
Representative of the true amount or of the data?
Okay, with the explanation is getting better. Representative of?
Consistent results.
Not so much.
Representative data.
Accurate is when you're given an exact or close to the exact answer, for example, we can say that clock is exactly at 8:12. Okay? Now, if it is not accurate, we could say, well, that clock is almost at 8:12. That almost is not making it accurate. See the difference? So accurate means that you're going to give an exact reading. In this case, it's going to be precise, term that you use, the precise reading. The number that you get represents precisely the amount of radiation that interacted with the ion chamber. Make sense?
Yeah. In the estimate, because it's a photon count, no, the voltage increase.
I haven't explained that.
Oh,
Okay, you asked me that, so I'll explain it to you. All right, so that's what happens, right? That's accurate. And so in this area, because the voltage is not too high, then you have the attractive force that you have will attract not at great speed, but it will attract the ions. When the voltage increases, okay, the reaction is the moment that a photon or a particle, say a beta particle, hits the gas, you create this, because of the attractive force, okay, you create this event. And so it's not accurate because in addition to having the first one event, you have multiple other events that are not created because of radiation. See? Everybody clear with that? In the case of the ion chamber, you're going to have one photon. That's what I was telling them. It's one photon, one molecule, two ions, or whatever many ions you can get out of the molecule. But it will be one molecule. In the case of when you begin to increase the voltage, what you have is you hit one molecule, but the ions that are created from the ionization event, they can interact with other molecules and have them split as well.
So with that, you're saying that the ionization chamber is more accurate than the other two, or?
Yes. Yes. I mean, from where we are. Yes. Yes.
So would it be true to say that, like, with the higher voltages, that it's more of an overestimation of how much is going on?
Yes, and remember, if we go back, if you read your notes from last time, I said Geiger Mullers are not used, they're only used to detect radiation, not to measure the amount of radiation. Remember that? And that's why, because you get many events, any ionization events, that are really not created directly by the radiation. Make sense? Now, proportional counters, and there's a whole variety of proportional counters, but proportional counters are used in many areas where radiation is used, but in labs it's used to, first and foremost, is to distinguish beta from alpha radiation. Getting some? Okay, that's the main thing. Write it down, it's important. Okay. With proportional counters, you have that ability. You can separate alpha from betas. And you're going, well, why is that important? I don't care, as long as well, it's two different ways. First, you need to know what they are so you can protect yourself, because the shielding that you use for both types of particles are very different. I talked about this before. Very different. So it is important for someone working in a lab that is using alpha and beta radiation. They need to know what is it that they are dealing with. How they are, say, for example, if you have a spill of something, you want to know what type of radiation it is so you can clean up accordingly. Okay? What type of protection you're going to give whoever is going to clean it. Make sense? And so it is important to separate between the two. Okay? Or if it is neutrons, then you need to know as well. Okay? And so proportional counters can do that. And they are also used to count activity. What is activity? Radioactivity. When you have, and this is not electromagnetic, this is particle radiation that I'm going to talk about here, proportional counters. so you have a seed of something. A seed is a radioactive material, okay? So you have a radioactive material, and you want to know what is the activity, because the activity goes down with time, right? Okay, that's called decay. Write it down. Okay, that's the activity. As time goes by, activity goes down, and so you have decay. So you want to know when you measure, okay, you want to measure where, in what stage is the seed that you're measuring. You know, does it has high activity, low activity, where is it? And then from there you can calculate the half-life of that radio compound. Okay? And you're going, well, why is that important? Well, it might not even be important to us in radiologic technology, but someone working with radioactive materials is important, because if it is, for example, if it is low activity, very low activity, it goes to a point that you can just dispose off. You don't have to send it to a special storage. You don't have to do anything, because the radioactivity is low enough or is zero activity. Are you following me? Okay. Is everybody understanding what I'm saying at proportional counters? Okay. Say, and this is just an example of how proportional counters might look like. They might be very simple, and they have, say, something made out of concrete, a couple concrete walls. Imagine a little house. And when I said a little model house, okay? This is made out of concrete. And what you have, you will place a proportional counter here. And then you can put your material, there is a dish plate, where you can put your radioactive material. And so you put it right above the proportional counter. The counter, what it's doing is counting how many times particles are hitting the counter. And then you have this connected to some kind of computer, and you have a monitor where you can see the activity of that compound or that radioactive material, whatever that is. Make sense? No?
Little bit.
Okay. All right. Anybody else? A little bit is good. All right. Okay, so it's important that you guys go back and take a look at the graph. All right. So let's take a look individually what we're gonna do. This is one example. Okay. Ionization chamber. Okay. Let me go back here for just a second. Ion chambers or ionization chambers, depending on where they are, if you make them very sensitive, you can detect, it is possible to detect particles, beta particles at least. Okay. If you have, for example, our ion chambers, the ones we were using the other day, they're just for electromagnetic radiation. They are not going to detect. You can put it right in front of a radioactive compound that is emitting betas or alphas. It's not going to detect. It just doesn't happen. Okay? It doesn't happen. So you need to make it more sensitive, and that's why when I said more sensitive, what am I saying? Increase the voltage. When you increase the voltage, now you can start detecting alphas and betas. Okay? And as you go on. So there are some ion chambers, and listen carefully, there are some ion chambers that if they are made sensitive enough, if the voltage is high enough, they can be used in laboratories to detect, you know, radiation spills and radiation contamination. Okay? And so, when we get here, the ion chamber, type of survey meter. This is just a type of survey. Some of them are used as type survey meters, and they're called the cutie pies. Okay? There you go. Let me show you what they look like. Yeah, that's what. This is what a cutie pie will look like. And so this is a handle. You put it right in front of the area that you think is contaminated, and it will give you a reading. Not very accurate, but it'll give you a reading that there is radiation present. Okay? In some cases, it could distinguish between gamma and beta. Okay? So let's go back. So that's now that you see what cutie pie looks like. Now, so it's both a rate meter device, measure exposure rate, used for area surveys and accurate integrating of cumulative exposure instrumentation. So in nuclear medicine, you're going to use a device just like I show you. This device measures X radiation and gamma radiation. And if equipped with a suitable window, it can also record beta radiation. Okay? So far so good?
And so what mean a suitable window?
A suitable window is the area. Did you see the ion chambers we used for our lab the other day? The little square things? It had a little round thing on top. That's the window. That's the area where radiation will go through. So in the case of beta particles, you need something very, very thin. Very thin, so it can go through, because these are particles, remember. And if you have something really thick, like cardboard, it was not going to make it through. Okay, so it has to be something very thin. A lot of times they will use very, extremely thin aluminum so to allow it to go through. Otherwise, they just don't go through. Yeah.
So this is going to be a little off topic. So basically, if one's working in an area full of beta particles, it would be best to wear cardboard sort of thing to protect yourself.
It depends. It depends. There are times where cardboard might be best than having lead. And sometimes, actually, the most common thing is plastic. Believe it or not, the different type of plastic you can use. All right, so that's what the window is. Okay, can measure radiation intensity ranges from 1 millirentgen per hour to several thousand rengens per hour. Okay, and in integrate mode, it can some exposure from as little as 1 Hz to as much as 1 Rentgen. So what it's doing is it's accumulating what it's reading, and it gives you a total reading. That's what the integrating mode is. Okay. So this will be more like it can give you, say, in a minute, how much radiation did we get in a minute, or how much radiation we get in an hour. So that's what the integrate mode is. Okay, this device can be used to monitor diagnostic X-ray installation when exposure times of a second or more are chosen to measure fluoroscopy scatter radiation exposure rates. So, for example, the ion chamber that we used, the 2 ion chambers that we used last time, they're used to look for exposure, okay, an exposure rate from an X-ray tube. They are not going to be very good. They are not sensitive enough to detect scattered radiation. Okay, it's not sensitive. It doesn't pick up. There are other ones that can be used to measure scattered radiation, or to measure leakage radiation from the X-ray tube, or to measure radiation escaping from X-ray room. So different, and I go back to what I had said before. You can have different designs, you can have different shapes, forms, and uses of ion chambers. Okay? That make sense, guys? Everybody? All right. Good. So advantages and disadvantages: able to measure a wide range of radiation exposure within a few seconds, okay, or milliseconds. Okay. The delicate detect relative large size of the unit, however, may be considered a disadvantage in some cases. I've seen some ion chambers that are just tiny ion chambers, and they work really well. Okay, so it depends on the use. Another disadvantage is that it needs without adequate warm-up time, its meter will drift and produce an inaccurate reading. So that's why it's important that if before you use it, you turn it on and let the molecules. Remember, you're dealing with a gas, and what happens with a gas when the temperature is high? Expands, right? Expands, the molecules become more active. And so you need to give them time to kind of recondition themselves. Also, what happens with gases when you change pressure? They can expand too, or they can compress, right? right? And so it is important that you let them kind of acclimate to the environment that you are. And so you have to turn them on, say, half an hour before, or 20 minutes before. So a little bit of time, just enough for it to get ready. Another important thing, another disadvantage that you have with ion chambers is that you can saturate the gas. What do I mean by saturation? If you keep exposing them, say in fluoro, where you have non-stop exposure to radiation, it gets to a point where all the gas molecules have been ionized. And you're saturated, you cannot do any more. You can have more exposure, but the thing is not going to give you any more readings. Make sense? And so it is important to also, after exposures, to kind of just let them settle a little bit. Give them a half a minute, I don't know. Depends on the unit. There are units that you don't really need to wait anything. So that's a disadvantage. It is most commonly used to measure exposure rates, millirentgen per hour, at various distances from a patient who has received radioactive materials or for diagnostic or therapeutic purposes. Okay, the device that I show you, this is a specific, and that's why I separated and I put it. Make sure you make a note of that, because I put this little portion here. I took it out of the middle of this whole paragraph, this area here. Have you noticed that in your notes? Look at it in your notes. I got it out, and I got it out because I don't want to confuse anybody with what I'm going to say. This device cannot be used to measure exposure produced by typical diagnostic procedures because of the exposure times are too short to permit the meter to respond. And I'm talking about it specifically of the cutie pie. So make yourself a note and say, this refers to the cutie pie. Okay, the cutie pie, you're not going to get that device and put it next to an X-ray tube. This is not going to do anything. It's not going to work. It's not sensitive enough. Make sense?
Mm-hmm.
So this is a specific for the cutie pie.
So we have this can. Oh wait, no, I don't know. No, sorry.
You have a hand?
Okay, no, we have it. I was getting confused with the previous slide, so never mind.
Mm-hmm. Okay. Everybody, are we good? Let's check. Let's make sure everybody understands. Hilda, explain as much as you can about an ion chamber to me. How do you understand it?
Like voltage.
How does it work? Under what principle does it work?
Like when the photon like hits the chamber, so it breaks the molecule into two ions, and those ions, the negative stays in the, I don't remember the name of the middle part. That's for the negative, and the positive goes to the bottom. But
Or the top.
Or the top. So, but
The
when
walls,
they are,
right? The wall of the chamber.
But they can, those ions can also interact with other molecules, breaking them and causing a chain reaction.
For ion chambers?
Yeah.
No. That chain reaction will not happen with ion chambers. It will happen with proportional counters and higher. Okay, everybody clear with that? Yeah? Okay. So, will you use, let me ask you this will be a test question, right? Will you use a proportional counter to measure radiation exposure from an X-ray tube?
No.
No. Okay, how about a Geiger Muller? No. Okay. Can we use an ion chamber? Say we walk into an area. Say you're just walking in and tell you, oh, there is radiation there, and you bring your ion chamber. Okay. You come and ask me, hey, can I borrow your ion chamber? Say, yeah, take it. Okay. I won't do that then. Take it. Will that help you if you're dealing with beta or alpha radiation?
No.
No. Okay.
Geiger Muller.
Okay. That makes sense, everybody? Hilda? So the ionization events that you were describing only happen with a proportional counter. But how about you? Why does it happen, Garrett? Why does the proportional counter is able to create that set of chain reactions?
Because increasing the voltage makes the detector more sensitive
Exactly,
to,
so
to
it's
different
voltage. So the
radiation.
key is there is voltage. By increasing more voltage. Okay. What was your question?
I was going to say that just to make sure I understood correctly. So if an ion chamber is made more sensitive, it can detect beta particles.
Yeah, it could.
Yeah.
If you can say, because all of these, when you look at this graph, all of these are regions. Okay. When you're getting to this area here, yeah.
Okay.
It could. Typically, it's not done that way. You use proportional counters, but it could. Yeah. A lot of times you want to buy a device that can help you in many areas. Okay. Are we good? Okay, good. Let's talk about proportional counters, okay, specifically. So the proportional counter serves no useful purpose in diagnostic imaging. It is generally used in a laboratory, to detect alpha and beta radiation, okay, and a small amount of other types of low-level radioactive contamination, okay. Maybe you're going to have, typically, write this down, typically this will not be used to measure or to count, say, neutrons. Okay, it is not good for that, but it's good for alpha and beta. That's the main thing. The proportional counter can discriminate between alpha and beta particles. I told you that. Okay. Now,
No, we don't want.
got it? One picture is enough.
Just
All right. So Geiger Muller. The Geiger Muller detector serves as a primary radiation survey instrument for area monitoring in nuclear medicine facilities. It's used everywhere. It's also used in nuclear power plants. It's used anywhere where you're going into an area where you suspect contamination, where you don't really care, you know, what the measurement is, what the accurate amount of radiation it is. All you want to know is there radiation here or not? Okay. With the exception of alpha particle emission, the unit is sensitive enough to detect individual particles. Except it can detect individual electrons emitted from certain radioactive materials or photons. So it can do gamma as well. Okay, that's what it's telling you. It can detect gamma, photons. It can detect X-rays. Okay, but it can detect, you know, one single particle. Geiger Muller detectors allow rapid monitoring. It can be used to locate a lost radioactive source or low-level radioactive contamination. Okay, a lot of times patients will be say a patient fecal matter, okay, it's a nuclear medicine exam, and they lose it in the bed, okay? So you have to go in with the Geiger Muller and see how far the contamination has stretched, okay? So here's where you're gonna use a Geiger Muller.
Yeah,
Okay.
and question. So, will that give you a number?
No.
It just says whether it's there or not.
I mean, it might give you something. They might have a meter. I'll show you a picture right now. It might have a meter that is not accurate.
Okay, I know when.
The main thing is it will go beep 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 beep, beep. Give you a reading or give you a light that is telling you, yeah, this is radiation. Stay, move away. Okay, make sense?
This means focus on detective.
What was it?
This means this is a focus on the detector. Because we
sorry.
have a two kind, it's a detector or measure.
Oh, this is to
This
detect.
detector.
This is a detector.
Detector.
Yeah.
And one question.
Uh-huh.
And this is they can detect every particle and photon, X-ray and gamma radiation.
Not very good. That's what I'm saying. With the exception of alpha particles, not very good for alpha particles.
Alpha.
Not very good. And the thing is with alpha particles, they don't go very far. Okay, and so you have to get really close to it. And by then, the person gets exposed a lot. So you don't want it like that. You want it to detect it, but you don't want the person to get exposed. So not very good with alpha. Let's see. Okay. Let's see what else. Okay, the quenching agent. Because the voltage with Geiger Muller's is so high, okay? The voltage is so high that you create a lot of molecules. And I'm sorry, you have the molecules, and the molecules ionize, and these ions break other molecules. And this can go on, okay? And it doesn't stop, okay? And you saturate the detector, okay? And so you add a quenching agent. The quenching agent will kind of slow down the molecules, okay? That makes sense? When I say slow down the molecules, you add another gas, basically. You inject another gas to the molecule, inject the gas, okay? That's the quenching. And so you don't have this chain reaction, okay? Because otherwise you turn on the Geiger Muller, it goes, and instead of going beep, 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 you go beep, and at that point it's saturated, it's not detecting anymore, okay? And so that's why you add the quenching agent. The resolving time. The resolving time is the time that it needs to, is the minimum time between the ionizations that can be detected, okay? So in between ionizations, you go beep, okay? And then you need a little bit of time to make the next detection. That makes sense? And that's called the resolving time.
So I don't understand because this exception, they can recognize the alpha particle.
Which part do you don't understand? The
Okay.
resolving time?
No, this part is because
Quenching?
Is it up? Yeah.
This?
Is it
Here?
Yeah.
Okay. The Geiger Muller detector allows rapid monitoring. It can be used to locate lost radioactive source or low level radioactive contamination. Okay. What part do you don't understand?
It's a why this is good for locate a lost radioactive source because it's not sensitive with the alpha particle emission.
Say for example, you place a seed on a patient. A seed, what is a seed again?
I think it's something very small.
In nuclear medicine, I talked about this before. In nuclear medicine, when they have a radioactive compound, and that radioactive compound goes into a patient, okay? Let's say they put a radioactive compound in someone's sigmoid area. The sigmoid is a common area for cancers, okay? That area, the rectum and the sigmoid, very common for cancers. So let's say they put a seed there, and they insert the seed there. The seed get dislodged, and you lose the seed. You cannot go into, if you flush the toilet, now you have radioactive compounds going everywhere, going into the sewer system. That's not a good thing. You don't want to lose that seed. Okay, so you have to find it. Okay, so now here's where you bring the Geiger Muller counter until you find it. Okay, and the closer you get, okay, the intensity goes up. Then the beeping goes beep 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 beep. Now it's higher and higher and higher. Make sense? Until you get to the, in this case, literally to the bottom of it. Okay, until you can retrieve the seed. Okay, that makes sense? Okay. I know it's hard for you guys to understand because we're working with electromagnetic radiation. But in labs, all kinds of labs, where they use radioactive compounds, they are not going to use X-ray machines. They use radioactive materials. Okay, you can have a piece of, say, uranium, Okay, uranium, you find it in mines, right? Okay, it's pitch blende and it's mixed with dirt. Okay, you get it out. How are you going to detect it? If you just see it, you don't see anything. Nothing happens to you right away. And so they will use something like this to detect what is being emitted. Okay, you can cut it into small pieces. Okay, cut it into small pieces, but you cannot lose one of those pieces. Okay, if it gets lost, you need to find it. And there is no other way to find it. I mean, you have to use a detector, a Geiger Muller. Okay. Once again, the amount of radiation is not going to be accurate, but you can get to the seed. You can get to the radioactive material. Yes.
You keep mentioning about preventing the device from getting saturated with radiation when it gets too much of it.
Yeah, saturated means you don't have any more gas molecules. Okay, the gas molecules have all been used up. Okay, and so it's saturated. Okay, and when you get saturated with information, it gets to a point where nothing gets to your brain anymore, right? You cannot absorb anymore. Okay, like 10 minutes before a test, you're saturated, and you still want to keep on reading. You're not gonna get anything. Your brain is saturated. That makes sense?
Okay.
Yeah. So the same thing happens here. The gas molecules are being used up.
And,
All right.
And the quenching agent, what does this kind of do?
The quenching agent, it slows down the molecules.
Okay.
And so the molecules are not too active, and so you don't end up with too many chain reactions. Remember, what's the chain reaction that I'm talking about, guys?
Like one photon causes a particle to become two ions, but then those two ions
Exactly, and
other
so the
reactions.
quenching agent will slow down that process. Okay? One more thing. Jesus, what is it resolving time?
It's the time that it takes for the detector to detect on another, to make another detection of the.
It's the time between one detection and the next. It's called the resolving time. Okay? And that is important because if you try to detect something else before that time, you're not gonna get it. And so you need time in between, and you need to know that. You know, typically it's in milliseconds. I mean, it's pretty quick, but you still need to know that.
And between the two time, the two detected time, we have a two presets.
No, it does it by itself. Yeah. All right, this is one type of what a Geiger Muller might look like. Actually, this is a proportional counter. And it's used in labs, and it's used for contamination in the spills. All right, TLDs, and you can see, make sure, okay, because I can sense you guys have not read this section in Bouchon. You need to read it, okay? Right, from the expressions that I'm getting, make sure you read. You have to read this whole chapter 36, but make sure you read before Friday. You need to read pages 557, 558, 559, 560, okay? All of them. And, yeah. Okay.
6, 7,
And
8.
I think Boucher has a little section on it, but you have to read it on Bouchon. This is,
Come on, 556.
he'll give you more. I gave you more than what Bouchon is giving you, but you need to read that. Okay, now we're going to finally. All right, TLDs. All right. So now we're going into measuring devices. Okay, these are not used. What we're going to look at next is not used to detect radiation, but they are used to measure the amount of radiation. What you use, okay, your dosimeters are TLDs. Okay, and so does it make any sounds? Does it emit light when you get exposed to radiation? No, you don't know when you get exposed. but you get a reading, right? Okay, so that's what TLDs do. TLD stands for thermoluminescent dosimeter. Okay, the TLD is the emission of light by a thermally stimulated crystal following irradiation. So what the crystal will do, it will absorb radiation, you expose it again, absorbs more radiation, expose it, absorbs this radiation. Okay, and it stores this radiation. Okay, and then when you bring these crystals and you heat up the crystals, they emit light, visible light, proportional to the amount of radiation that it had stored. Make sense? Okay. All right, the crystals that are used, the most common crystals are lithium fluoride, but also calcium fluoride has been used and calcium sulfate. The most common is lithium fluoride. All right, so this is the basic idea, okay? Let's say this is lithium fluoride. You expose it to X-rays, and it absorbs the radiation. You know, the companies state that they can be used, some of these compounds can be good for 3 months, meaning that you can accumulate radiation for 3 months. I don't know, I prefer it to be more like 2 months. All right, and then when it's ready for reading, you take it to a lab, they heat up the lithium fluoride, emits light, and now you have a photomultiplier here. What is the purpose of the photomultiplier?
It amplifies the signal.
Nope. Function of the photomultiplier. Have you ever heard that term, photomultiplier?
Yes, I.
Yes,
have.
where? When?
Yes.
Yeah, with CR, right? Laser, and then the plate emits light, you have a photomultiplier, right?
Yeah.
Okay, so what's the function of the photomultiplier?
Okay, I'll just go right.
Change analog.
No, I'll just say
First and foremost, photomultiplier, what it will do, it will turn the visible light into an electrical signal. Okay? So it turns the light into an electrical signal. That signal can be sent to a device that it can read that signal. What signal am I talking about?
The
Make sure.
alternating
The light being released.
analog signal.
The electrical signal.
The analog.
Electrical signal.
Electrical
Yeah.
signal is analog.
Huh?
It's electron signal, it means analog signal.
Yeah, yeah. You can make it digital if you want, but you know. But the point here, what is important? The key here is that the photomultiplier will turn visible light into electrons, and when you have collected enough electrons, and they are flowing, what is that called? Current. There you go. Woo! All right, and now you can read that, right? Okay. So that's the function. This is pretty much a cutoff of the device they use to do the readings. Okay, they stick. This is a photomultiplier tube here, and then they have a planchet here, and that emits heat. You put the lithium fluoride here, you heat it up, and then the photomultiplier detects it, and you can send the signal out. Okay, it works very well. It's been used for years. Any questions before we leave? No? Okay. All right, quiz on Friday, by the way. Yes. I want to make sure that you guys read the pages I told you. I'm beginning to not trust you.